Okay, good evening, everyone. So we'll wait for others to join in. We'll start at 4. Okay. Good evening.
Good evening, sir.
What's going on in school?
So we are doing geometric optic. We're going to start geometric optics numericals, and we are still doing electrostatics. We started electrostatics 2 today.
Okay. So you're able to follow, right?
Yeah, yes, sir.
All right. It's already 4. Waiting for. Still, I think at least 10 students haven't joined yet. You guys have done the assignments?
Yes, sir. Yes, sir.
Okay. And when is your next Kimon test? You know that?
21st. Next week, Sunday.
21st.
Yes, sir.
Okay.
Yes, sir.
All right, so let us start. Others will join meanwhile. So today we will have a second session on moving charges and magnetism chapter. Fine. So today probably we'll be able to complete this chapter. If not, it will spill over a little bit on the next class. Fine. So the last session, our focus was how to find the magnetic field by different types of current, right? Straight line current, circular current, whatever kinds of current were there, we are trying to find the magnetic field because of that. Using which law we have found magnetic field? Biot-Savart law we have used to find the magnetic field. All right. Now in today's session, our focus is what will happen to the current in already existing magnetic field. Magnetic field is there, fine. So if magnetic field is there, what will be the force or torque? What is the effect of the external magnetic field on the existing current? Fine. So that is actually the first part of the chapter. The name is moving charges and magnetism. So we have learned magnetism before. Before we have learned magnetism, now we are learning moving charges, how it get affected by the external magnetic field. Fine. Now, if I know what will happen to the moving charges, I will know what will happen to the current also, because current is nothing but moving charge only. Fine. So the first thing that we are going to learn in this section, write down, is Lorentz force. Write down. So Lorentz is the name of the person who has identified or discovered the formula for the force on the moving charge because of external magnetic field. So Lorentz force gives us the net force on a charge due to external electric field and magnetic field both. So it will give you total field, total force. Fine. Now, if the charge is moving, will there be a magnetic field because of the moving charge or not? If charge moves, will it create its own magnetic field or not?
Yes, sir.
Yes.
Right? It will create its own magnetic field. But we are not bothered about this. Okay, what we are bothered about is that there is an external magnetic field. There is an external magnetic field and electric field. So whatever electric field and magnetic field is created by the charge, that will not affect the charge. It's like you cannot apply force on yourself. If you apply force on yourself, there will be equal and opposite force on you only. So net force will become zero. Similarly, the charge, when it moves, whatever electric and magnetic field the charge creates, that cannot apply force on the charge itself. Fine. So that own magnetic field and own electric field you should not consider. So what will happen is that there might be an external electric and magnetic field that will create a force on the moving charge. Fine. So it has to be external. Fine. So the Lorentz has given us this formula. Force is equal to Q times E vector plus Q times V cross B. Okay. So this is the total force on a moving charge because of external electric and magnetic field. All right. Now, this part of the formula we have already discussed, Q into E. So our main discussion will be around this. This is referred as magnetic force. This is the magnetic force. Fine. So let's focus on that for some time. So magnetic force, FB you can say, is QV cross B. Now both V and B are vector quantities. All right. And there should be a cross product between V and B. So what I can say about the direction of the force due to the magnetic field B? Anyone? What I can say about the direction of magnetic force because of B?
Perpendicular to B and B.
Perpendicular to?
B and B.
B and B.
Perpendicular to V and B, right? Very simple. Just like any other cross product will be perpendicular to both the vectors. Similarly, the force will be perpendicular to both V and B. Okay, so we will write a few points to note. First point, write down. Okay, so if Q changes sign, force will be in opposite direction. Then what does it mean? It means that suppose on positive charge, force is this way. Now if you replace positive charge with a negative charge, force will be in opposite direction. Very simple. Okay, because minus will come in. Second one is whatever you have just said, that the force will be perpendicular to both V and B. Okay. And can you tell me when the force will be zero? In what situation force will be zero? Force will be 0 if anyone.
If V and B are parallel or anti-parallel.
Okay, V and B are parallel or anti-parallel, or velocity is 0, or B, magnetic field is 0. So if charge is at rest, this is very important, okay? If charge is at rest, magnetic force will be 0. It doesn't matter what is the direction of magnetic field and anything else. So velocity must be non-zero. This is must for magnetic force to be present. Okay, this is most important thing. If charge is not moving, charge is at rest, it will not experience any magnetic force. Will it experience electrostatic force, everyone? Will it experience Q into E? If velocity is 0, will it experience this force, Q into E?
Yes, sir.
Yes, sir.
It will experience, because electric force doesn't depend on velocity. Okay. Now, using this Lorentz force, you can actually get the dimension of magnetic field also. So, F is equal to Q V cross B. So, dimension of force is equal to dimension of charge into dimension of velocity into dimension of magnetic field. Okay. So, dimension of force is what? Mass and acceleration, ml t minus 2. Dimension of Q is current, which is ampere into time. Velocity is L into t minus 1. This is the magnetic field B. So dimension of magnetic field B is equal to M L t minus 2 A minus 1. Okay, so this is the dimension of magnetic field. Okay.
Sir,
Sir,
why
length
L,
only.
sir?
What?
Why L?
L is also gone, right? Even L is gone. Sorry. L is gone. Now it is fine.
And it will be T minus 1. No, correct.
What? This T is gone.
Yes, sir. Yes, sir. Correct.
T is gone. Then this L is gone. Fine. No doubts, right? Okay. So
Right.
now let us talk
Sir,
about.
sir, could you go back to the previous page 1 minute? My connection is bad.
What happened?
My connection went off. Could you go back to the previous page 1 minute?
Fine. So let's proceed now.
Yes, sir. Got it. Thank you, sir.
Now, suppose the charge is moving in only the magnetic field. All right. And I want to find out how much work the magnetic field does when the charge is moving. Okay. So can you find out that, suppose the force is QV cross B. Okay. The small amount of work done by this force will be F dot dr. So can you find out how much it is? dW is what? Can you simplify it and get the answer? All of you tried? Okay, let me do it now. Force is Q V cross B dot dr. Can I write velocity in terms of dr? What v will be? Wait, dr by dt, right? Forgot? This dot with dr. Now tell me what is the value of this? Everyone, dr cross b dot with dr. How much it is? Right hand side is what?
0.
Who said?
Because it will be perpendicular.
See, dr cross b will be perpendicular to dr, and you're taking dot product with dr, so it will be equal to 0. dw is 0. Understand, all of you? dr cross b is perpendicular to dr. So taking dot product with a vector dr and another vector that is perpendicular to dr. So two vectors perpendicular to each other, then the dot product between them will be 0. So dw is 0. So when you integrate from initial to final point, that will also come out to be 0. So this is very important. Work done, write down, work done by magnetic field. Work done by the magnetic field on a moving charge. Magnetic field can do the work, but on moving charge, it cannot do the work. Fine. So work done by the magnetic field on a moving charge will be always 0. So can you answer me one thing? Can magnetic field B change the kinetic energy of moving charge? Anyone? Can it change the kinetic energy of moving charge if only magnetic force is being applied?
No, sir.
No, sir.
No, because the work done is change in kinetic energy. So if work done is 0, change in kinetic energy is also 0. So can I say that the magnitude of velocity will be constant? Because kinetic energy is half mv square. Mass, I'm assuming, doesn't change. So what will happen is that if half mv square, this is the kinetic energy of a charge of mass m. If this is constant, this automatically implies that in a magnetic field, in an external magnetic field, the magnitude of velocity should be constant. Direction can change. Okay, that is fine. Direction can change. But if only magnetic force is existing, the magnitude of velocity for the moving charge will not change. So magnitude of initial velocity should be equal to magnitude of the final velocity. So this is a trick to solve few of the questions that you might see later on. All right, so keeping these, tell me.
So the magnitude is constant, but the direction can be changed, sir.
Yes.
Okay.
Direction can be changed. You will see this in this example. So keeping these things in mind, let us talk a little bit more about the motion of the moving charge in a magnetic field, how it should move. Okay, so suppose there is a situation, this is the velocity, okay, this is the velocity of the charge. Charge Q has this velocity V, fine, and magnetic field is everywhere like this. Magnetic field comes out. So which direction it will experience the force? Force, I'll write down again, Q, V cross B. Which direction this charge will experience the force?
Sir, upwards.
Upwards.
Y-axis.
Upwards. Okay. Others? You know how to take cross product? Align your hand in the direction of velocity, then curl your finger in the direction of magnetic field. Thumb is the direction of the cross product between V and B. Where it comes?
So perpendicular to V, downwards.
Downwards, right?
Yes, sir.
Everyone. Align your hand like this, like that, then curl your finger outwards. Thumb will be showing down. Check that. But if you align like this, then you have to curl the finger goes inside the screen, then thumb is up. So if magnetic field is inside, then thumb is up. Everybody understood? Okay. Now here the assumption is charge Q is positive. If charge Q is negative, then it will be upward force. Okay. Now you are applying downward force. What will happen to this velocity? Will it change the direction? What do you think? What will happen? It will slightly tilt like that. Right? Now suppose it changes its velocity. Now tell me which direction the magnetic force will be. Will it remain in the same direction or the magnetic force will change the direction? Everyone.
It will change.
So it'll change.
Which direction?
Be
So
perpendicular to
It'll be
the velocity
perpendicular to
vector.
that.
Perpendicular to the new velocity vector like this, isn't it? So now what will happen? It will further bend. Let's say it bends like this. Okay. Now which direction the force will be? Q V cross B. V cross B. It will be on the left hand side now, like this, right? Then it will bend like that. Again, the magnetic force direction is continuously adjusting itself. It every time remains perpendicular to the velocity. Now I am drawing in a step-by-step manner, but in reality it is a continuous change, right? So because it will be a continuous change, you need to create a continuous curve. All right. So can you think of a motion in which force is always perpendicular to the velocity?
Circular motion.
Circular.
Circular motion, right? So exactly that will happen here. Okay. So write down if the initial velocity, if the initial velocity is perpendicular to the magnetic field, then the charge will describe a circle. The reason, the force has to be perpendicular to velocity all the time, and there is no other motion other than circular motion for which that is true. Okay. So if magnetic field is like this, okay, if magnetic field is inwards, everywhere it is inwards, sorry, not inwards, outwards, like that. Okay. So can you tell me whether the velocity will be like this or like that for a positive charge?
So towards the right, no, sir. Clockwise.
How?
So it's the same as the previous case.
No, logic. You should don't correlate.
Yes, sir. Like that only, sir. We can take the cross product and
Cross
the
product
force has to
direction
be.
should be in the direction of what?
So the cross product between velocity and B should be in perpendicular to V.
So,
Inwards, into the circle it should be. Towards
So-
the center of the circle.
correct. So basically the direction of force should be in the direction of radius, in the direction of radius or towards the center. So your thumb should point towards the center. That is the direction of force in the circular motion. Okay. So if it goes on that side, then only thumb will point towards the center. If it goes like this, then it will not be like this kind of circle. Okay. If it goes like this, then what will happen? Where the center should be? If it goes like this, the center should be where? Over here or over there?
Sir, up.
Upwards. So what will happen is that if you go in that side, the circle will be like this. Okay, circle will be upwards then. The difference is one is clockwise moving, other is anti-clockwise movement. Okay. So these are the few basic geometrical things you need to take care of. Okay. Now, if this is happening, all right, then I will draw the magnetic field few other places. Magnetic field is coming out. Let's say magnetic field is B. B is the magnetic field. Okay, speed of the charge is V, charge magnitude is Q, and the mass of the charge is M. Okay, I want to find out the radius of this circle. Try finding it out. Everyone, try this. See, if there is a force in a circular motion, what should that be equal to in terms of velocity?
Centripetal.
Centripetal force in a circular motion should be equal to mv square by r, right? Now do it. So basically Q V cross B. Now V cross B is equal to magnitude of V into magnitude of B into sine of angle between V and B. What is the angle between velocity and magnetic field everywhere?
90.
90. So it is Q V into B only. This is the force. This should be equal to M V square by the radius R. So radius will be equal to mv by qb. All right, so remember this. But what is the condition here? Can you tell me what is the condition here? Velocity should be perpendicular to magnetic field. Remember that. Okay, so this is a special case in which velocity is perpendicular to the magnetic field. What if velocity is having some component which is parallel to magnetic field? Then what will happen? Okay, so we will take that example. suppose magnetic field is like this, upwards. This is how magnetic field is in your plane only. This is the magnetic field B, and this is your velocity, like this. This angle is theta, velocity is V. All right, now this velocity will have how many components? Two components you can take. One will be along the magnetic field and one will be perpendicular to the magnetic field, right? So along the magnetic field, what will be this component? V into
Cos.
V cos theta. This will be equal to V sin theta. Okay. So in this scenario, what will happen is that because of V sin theta, charge tries to move in a circle. Okay. Whereas V cos theta movement remains constant. So along the direction of B, there is no force. So the particle, while it is moving in a circle, has to move up with V cos theta velocity also. So what kind of motion can you think of? How it will move? While moving in a circle, it will move up. So what it will be? How it will be?
So ellipse.
Helix, right? It will be helix. It goes like this and also moves up. It also moves up like that. Fine. So if you look from the top, it will look like a circular motion. You'll not be able to see the movement. This movement you'll not be able to see if you look from the top. But then it will move up with a speed of V cos theta. Fine. So let's decode this motion a little bit. So basically I'm saying that V perpendicular is V sin theta and V parallel to the magnetic field is V cos theta. So if you look from the top, okay, can you tell me what will be the radius of the circle? Everyone?
V sin theta by QB.
Everyone, the particle moves in a circle because of the perpendicular component, right? So m into V sin theta by QB. Okay, this is equal to m V perpendicular divided by QB. Okay, fine. Right. QB sin theta, you said. Wait. Somebody. No, Shamik, sin theta in the numerator, not in the denominator. Okay, now tell me, in the previous case, this one, we'll go back to that case once you find this thing here. Find out the time period of revolution, how much time it'll take to complete one revolution, everyone. In this case, the simple case in which it is moving in a circle only, what is the time period of revolution? T is equal to what? Everyone, time period in a circular motion 2 pi r by the speed, right? This is the time period of revolution. So you'll get t is equal to 2 pi m by qb. Everyone is getting this? All of you?
Yes, sir.
Now tell me, what is something amazing about this time period expression? There is something which is very weird about this time period.
Doesn't depend on the speed or radius.
Correct. It doesn't matter how fast the charge is moving. Time period will be fixed. Doesn't matter what is the
Sir,
velocity.
isn't because the radius will also be more especially.
So it doesn't matter what is the velocity of the charge. It will complete the revolution in this much time only. And like what Siddharth said, that is possible only when the distance covered will be increased if you increase the velocity. So what will happen? The radius increases. If you increase the velocity, radius increases, but time period of revolution remains same. Okay, now come back to this case. In this case, what is the time period of revolution? Shashank, understood? Radius increases, perimeter increases. What is the time period revolution here? 2 pi r by which velocity?
V sin theta only, sir.
2 pi r by v sin theta only, because v sin theta is the tangential velocity along the circle. That is the velocity with which it is describing the circle, or the speed with which it is describing the circle, v sin theta only. So here also time period remains same, 2 pi m by qb, or omega, which is angular velocity, 2 pi by t. You'll understand that this is useful in higher order question, which you'll be solving later on. qb by m. So angular velocity will be fixed because time period is fixed. Okay, fine. Now tell me how much it moves ahead in the direction of magnetic field by the time it completes one revolution. That is called pitch. Pitch is the movement along magnetic field in one revolution. This is not SHM, Aditya. This is circular motion. Omega in SHM is angular frequency, not angular velocity. Correct. So pitch P is the parallel component of velocity into time period, right? So that is 2 pi m by qb multiplied by v cos theta. This is the pitch. Pitch also means that, you know, if it starts from this point, by the time it completes a revolution, one revolution, it will again hit the same point on the same axis in one revolution. Fine. So all of this will be useful when you will be solving numericals. Right now it is just like a theory, right? Is there any doubt? Anyone has any doubts here? So we will take a couple of numericals now. Um, this one, what is the answer? It's a fill in the blanks. Everyone should answer. Okay. See, it's about radius only here. And one more thing you have to notice is that D is going in other direction, whereas A and B are going in that direction. So definitely, charges are opposite. D's charge is opposite of A and B. So neutron, proton, electron, and alpha. So electron is the only one odd man out here. So D has to be electron. So like this, you can arrive at the answer, but that is like tricking the question itself. So let's do it properly. So the force is equal to QV cross D. Okay. So uh, all of them enter like this. They enter like this. So which direction V cross B is? Everyone, V cross B direction is what? If this is the velocity.
Right side.
V cross B, everyone, right or left?
Right, sir.
Align your right hand in the direction of velocity, then curl it inside, goes inside. So thumb is on the left hand side, right? So V cross B is this way. So center has to be here. But then for negative charge, the force will be in opposite direction if Q is negative. So that is why D has to be electron. This is D. Alpha particle follows which one? Now I have to pick between A and B. So I know the radius is mv by qb. So A and B can be either proton or alpha. Now for the alpha, radius of alpha, mass of the alpha is 4 times mass of the proton, that into velocity v, divided by charge is 2 times the charge of the proton. Okay, so radius of alpha is 2 times the radius of the proton for the same velocity. Okay, so B has to be the alpha, because B has the higher radius. Okay. All right, so I can see many of you have got it correct. One. Okay. All right. So people are picking all sorts of options. Let's have a poll quickly. What do you think? Second one, what is the answer? All right. So this is what people feel. Option B is majority. Let's see. Two particles A and B, Ma and B, same charge. They have the same charge. Uniform magnetic field. Speeds are V and VB. Then what? See, clearly radius of A is greater than radius of B. Okay, that is the first thing that will come in your mind, right? Radius of A is greater than radius of B. Radius of A is mass of A into velocity of A divided by Q into B. That has to be greater than mass of B, velocity of B divided by Q into B. Okay, so charges are same, so this will get cancelled away. MAVA should be greater than MBVB. So direct question came in JEE Mains, so you can see what kind of questions are asked. Class 12 chapters are very simple and straightforward. This one. Anyone? No one? One thing that you should notice here is that the particle remains in xy plane. And since the particle remains in the xy plane only, I can say that the force is experienced in the xy plane itself. Okay, the force component in the k direction is 0. There should not be any force in the direction of k, otherwise the charge particle will come out of the plane. Fine. So keeping that in mind, and also it is not circular, so electric field you know need not be 0. Let me solve it now. So what is given is velocity. Okay, velocity vector is, let's say, v naught I cap. Fine. So when I find the magnitude of the force, which is what, QE plus QV cross B, the component of the k direction, the component of k should be equal to 0. Velocity in k direction should be 0. Okay, so let's take option A. Let's evaluate it. Q is 0 because E is 0 for A, and V cross B. V cross B is what? Q into V into C I cross K. I cross K is minus J. This comes in. All right. So this is the direction of force, and the particle will try to go down like this, but it will also try to cover forward distance. It will try to go like this in a helical path. Okay, so this appears to be fine. If you look at the option B, the force is equal to QAI plus Q I cross K is minus J, like this. And yeah, this is what it is. So even this appears to be fine because the force is coming in the direction of AI minus CJ. Okay. So this appears to be correct. And if you look at the C, option, what is the difference between A and C? B is BI. Acha, okay, that's a difference. So over here, if you do Q V cross B, there will be a K component coming in. So it cannot be true. All right. And over there also, if you do I cross J, K will come in. So these two cannot be true. All right. Now we have to pick between A and B. So which one do you think it is? And why not B? If you say A is correct, why not B?
Sir, in B, the force will not suit this motion. The force will be almost along the motion of the particle.
But there is a force downward also, right? Minus CK, minus QCJ.
Yes, sir, but if you draw the vector, it will be AI minus CJ will be inclined towards the x-axis also, no, sir. So that won't be perpendicular to this motion.
AI minus CJ. Okay, what you mean to say is that if you draw a perpendicular from here, it should hit the center, right? So it has to be tangential. This velocity has to be tangential, and this is the way it should bend like this. Correct. So that is how you can arrive at option A. Okay. It shouldn't be B because J is negative. No, J can be negative, Ayush. J can be negative. Why not? In this case, also J is negative only, isn't it? But the logic is that the force is tangential to the velocity. You can see that velocity comes tangentially from that point.
Sir, can you repeat,
Sir?
sir, why A is
Why what?
why we chose A
We
instead
chose
of
A because the force should be in the direction of the center. Okay, center of the circle. Now this is a helical path actually. It goes like this, it moves forward. But then over here the velocity is tangential and then it bends like this. Okay, the force has to be perpendicular to this initial velocity.
Sir, can you explain again why you ruled out C and D?
C and D because Q V cross B, if you do, the force comes out in the direction of K also. There's CJ, right? There's CJ and BJ. So I cross J is K, right? So force will come out to be in K. So the charge will come out of the screen. It will no longer remain in XY plane.
Okay, sir.
Force has to be in I or J direction.
Sir, sorry, sir. One more doubt.
Huh.
Sir, you said because the force is perpendicular to the initial V. But then even in the second option, one part of the force is still yeah, one part of the force is still perpendicular to initial V, no, sir. When you resolve it into
No, entire force has to be. Because you can see how velocity is coming in. You can see here the velocity is tangent to the velocity is like this, right? The force has to be like that.
okay.
Sir, but then it is given the velocity is found to be like it's non-circular. So if it is perpendicular to the initial velocity, it should be circular, no, sir?
It is not circular, it is helical. It is moving forward also. It's going like this.
Oh, okay, okay. Yes, sir, yes.
It has a component of velocity in the direction of magnetic field.
So, but shouldn't there be some electric field, sir? Because in A, it's zero, but for non-circular, there should be some electric field, no, sir?
Not required. The helicals are not you see, helicals are they are not circle. Okay, helix is not a circle. Depends how you're looking at it. For example, this one, um, if you're looking from the top, then it looks like a circle. If you look from here, will it look like a circle? Who asking that? Kirtana, I'm talking to you.
Yes, sir. Yeah, got it, sir. Got it.
Okay, next up. Um, this one. Okay, Shaumit got it. Others?
Single correct, multiple correct.
Multiple correct. Whenever there is a doubt, assume it to be multiple correct. Okay, I'll do it now. How it will try to move? The particle goes in like this. Will it curve like this or will it curve down like that? Which one?
Upwards.
Upward.
Upward.
Upward, right? It's a positive charge, isn't it? No, it is not written. It is not written. It can be negative also. So both are possible, downward or upward. But you can consider, because scenario should be neutral, so I can assume anything, positive or negative. So I'll assume it to be positively charged. Now, if it has to not, if it doesn't crosses region 3, then what should happen? It goes like
It should
this.
turn around.
It turns around just on that point. So basically, this distance should be what? L should be equal to the radius, right? So if L is greater than the radius, the particle will not be able to enter the region 3. All of you agree this? Everyone?
Yes, sir.
Others, you did not understand? Everyone?
Yes, sir. Yes, sir.
Okay, so length should be greater than the radius, which is mv by qb. Fine. So velocity should be less than qbl by m. This should be the velocity for which the particle doesn't enter. Okay, this is true so that it doesn't enter. If it has to enter, it has to be greater than QLB by M. So B is not true. Path length of region 2 is maximum when velocity is this. Region 2 path will be maximum when velocity is that. Now, is it true? The C part, is it true?
So,
What if velocity is very high? If velocity is very high, it will go like this. What will happen there? Will it come back after that? On this point, what happens?
It'll enter region 3.
Go straight.
What will happen at that point, everyone?
Will continue
It
going.
It
continues
will go
in that
tangentially.
direction.
It will go tangentially. Magnetic field is not there. So due to inertia, it will go tangentially. Why it will come back? Fine. So yes, it is true that if the radius is such that r is equal to L, then it will spend maximum amount of length inside the region 2. That's why C is correct. Time spent in region 2 is same for any velocity as long as it is returning to region 1. Is it fine? D1?
Yes, sir.
Time period for a full circle is 2 pi m by qb. If it returns, it means in region 2, it is covering half the circle, right? Half the circle. So it will spend pi m by qb time. Got it? If velocity is lesser, it will just go like this and come back. Every time it is covering half the circle. Every time it covers half the circle. Okay? If you keep on increasing the velocity. And time for that will be fixed. So that's why D is also correct. So A, C, D, 3 things are correct here. Okay, so just one more question on this concept, then we'll move forward. Any doubts here? Anyone has any doubts? All right. Okay, so the question is like this. there is a magnetic field which goes into the plane like this. Okay, this distance is d. Fine. Now, if a charged particle comes like that, it's a positive charge, okay, with velocity v. Now, the d is actually greater than mv by qb. So the charged particle, how it will travel? It will go upward or downward? Positive charge.
Upward.
Upward. So it goes like this. Okay, it goes like that, and then it hits here. After that, it goes like this, tangentially outwards. Okay, you need to find out.
So the D is greater than D.
Sorry, D is less. D is great. Less. Okay. So you need to find out the deviation angle from initial velocity. Basically, I'm talking about angle between the initial velocity and the final velocity. So this angle, we extend this line like that. I'm asking you, what is this angle? Okay, how much it is? Theta is what? Are you able to proceed? Should I help? Should I do it? Everyone, Tripan, Ayush, Siddharth.
Sir, 1 minute. Sir.
Should I give you hints? Chalo, hint deta hu. Many are maybe. So if you drop perpendicular from here and drop a perpendicular there from the line of velocity, you'll get the center. The intersection of this line and perpendicular on that line over here will be the center. And radius, you know what it is. This is radius R. This is a center O. Okay. Now, can you tell me what is this angle? Anyone? How much is that angle? Okay. Others?
So theta.
Theta only, right? It's theta. You can see here. Draw a line like that. This chapter is full of geometry. This angle is theta. This is 90. 91 is theta. 90. So this angle is theta. Okay. Now do it. Just write down the equations. Are you able to proceed now? Okay, I'll write it now. All right, I think some of you have got the answer. Great. So over here, R sine theta. R sine theta should be equal to D. Yes or no? This is R, right angle triangle. So R sine theta should be equal to D. And what is R? MV by QB. Sine theta should be equal to D. So sine theta should be equal to QBD divided by M into V. Okay. So theta is sine inverse of that quantity. If this quantity is greater than 1, it means that the particle doesn't come out. Okay. Automatically that will be taken care of from this expression. All right. So this is how you deal with this particular question. We'll be taking other questions at the end. Let's proceed with the theory part. Write down cyclotron. So cyclotron is a device. It's a device to accelerate the charges. So sometimes you need to conduct experiments in which you are bombarding the subatomic particles traveling in high velocities and see what will come out. So when you collide subatomic particles, maybe pi bosons and other particles may come out. So first you need to accelerate them, and then only these particles will collide. Okay. Yes. Fine. So let's draw and see how does it look like in a experimental setup. So all of you try drawing this with me. So you need to first draw D's. D's as in, you know how D looks like. Um, this is a D. Okay. You need to draw two D's, and the other D is actually inverted D. You don't need to be very accurate with all of this. You can draw it from hand. So you get two D's like that. Then first we are drawing, okay? Then we'll understand what is this D and all of these instruments. So first we'll construct everything. This box at the bottom, this is known as oscillator. You'll understand why it is called so. Okay. Then you have this zone. This zone is having magnetic field. Magnetic field out of your screen. So that magnetic field is represented by dots. So all of you put dots along this rectangle. Actually, it is dot with a circle, but even dot is fine. Okay. So this implies the magnetic field is out of the plane. Okay. Now over here at the center, okay, at the center, you're having a charge. Fine. Now this charge, what we'll do is that we'll first draw the path of it, then we'll understand in more detail. First, all of you draw this. It's a spiral kind of path it'll follow inside this cyclotron, like this, and then will come out. Okay, fine. There is a deflector here. We'll not get into the technical details of how deflector works and all that. Deflector does just make sure that the particle comes out after some time in a proper way. Fine. Now, what are these D's made up of? And what are these instruments that we have drawn? Let's talk about this. So these are nothing but, these are metallic enclosure. Write down. They are metallic enclosure. They are 3D enclosures. Fine. So if you look at this is how it will be. This is how the D is. It's a 3D object, but when you look at it from the front, it looks like a sheet only, but that's not true. It's a 3-dimensional object. Okay, this is the plane, and there is this 3-dimensional thing. Fine. And two Ds are there. They're metallic enclosures. And why they are metallic enclosure? Because you want to have electrostatic shielding inside it. Electrostatic shielding inside the Ds. So when charge particle goes inside the, so basically when a charge goes inside, it cannot experience any external electric field. Okay, that's what electrostatic shielding is. Inside an enclosure, electric field will be zero from outside. So now electric field is coming in. So from where electric field is coming? Electric field is coming from this oscillator. Oscillator can be like a battery that switches the polarity. Okay, it switches the polarity. What will happen is that initially, let's say this is positive potential, this is negative potential. Immediately after, this will become negative, other one will become positive. So the potential keeps on fluctuating. First, the right hand side D is higher potential, then left hand side will become higher potential. So like that will happen. Now, when there is a potential difference, not actually, Ayush. It's a step function. So it is not that the battery potential magnitude is slowly decreasing to zero, then becoming negative. Immediately it will become positive, +5, then immediately it become -5, like that. Okay. So basically, when you have, the D's are there, so the faces of the D's are they're facing like this. The D's, the right hand side D face is this, left hand side is that. These are two faces facing each other, metallic ones. They act like a capacitor. So when there's a potential difference between the faces, there'll be electric field between the face. Okay. Hold on, Anirudh. Hold on. You'll understand everything. Fine. Why polarity switches? I'm coming to that. Hold on. So when there is an electric field, let's say this is higher potential, this is negative potential. Electric field is like this right now. And when polarity switches, the electric field direction changes like that. Okay. So basically what oscillator does is, oscillator changes the direction of electric field between the phases after every some interval of time. Now someone is asking why we are switching the polarity, and the answer to that is this one, that these oscillators are very close, sorry, these are very close to each other. Okay, so it is as if the charge is moving in a circle only. Fine, charge moves in a circle, so I exactly know what is the time period of revolution. It doesn't matter what is the velocity of the charge. I know in how much time the charge goes inside the D and comes out of the D. Getting it? So basically, when charge is here trying to go on the left hand side, okay, I am switching on the electric field in this direction. So charge's velocity increases. And once it goes inside the D, electric field is zero inside, electrostatic shielding. So it will have no effect because of, it has no effect, the electric field has no effect inside the D once the charge goes inside the D. But magnetic field has effect. So it will move in a semicircle inside the D, and I know that it comes out of the semicircle in a time which is pi m by qb. Right? 2 pi m by qb is the full circle's time. So when it goes inside the D, it comes out half the time period, and when it comes out, I will switch the polarity. and electric field is now this way. So now the charge will accelerate when it comes out of the left hand side D. So its velocity increases, and when velocity increases, now the radius on the other D will be higher because radius is mv by qb. So it will describe a higher radius on the right hand side, then again comes out in pi m by qb time, and when it comes out, again I switch the polarity, and then again it accelerates, and when it accelerates, the radius further increases. All of you have understood now the functioning of cyclotron, how it works, everyone?
Sir, could you repeat?
What could you repeat? Tell me, what is the issue?
The way it accelerates.
What is the doubt? Doubt is what? Exactly, pinpointed doubt.
Sir, I didn't understand when the oscillator changes the polarity, how does it accelerate?
Acceleration happens because of electric field. All of you understand that magnetic field cannot change the magnitude of velocity. Everyone got it?
Yes.
Magnetic field cannot change the magnitude of velocity. If you want to increase the magnitude of velocity, electric field should be there, right? Now what happens is, let's say the charge is inside the D. It comes out from the D, and then electric field is in this direction. So velocity increases when it goes in the direction of electric field, because electric field will do the work. So the velocity increases, radius also increases, and then when it comes out from here, earlier electric field was in this direction. Now I'll switch the direction this way. So it will accelerate further. Its velocity increases further. So radius increases further. And then when it comes out from here, again I will change the direction of electric field in this way. So again it will accelerate. Acceleration happens between the D's only. Clear, Manjunath?
Yes, sir.
Everybody? This is
Well,
very
sir,
important. Huh?
So the D's have, they're like,
Hollow.
there's no, is there a, it's hollow, and sir, you said that there are plates, no, sir? So then
You
how
are
does
wondering
the
whether charge
particle
will hit the
enter?
plate.
So how does it enter? Yes, sir.
So you have done that Rutherford experiment.
Oh, okay.
In
Charge will
Rutherford
go through.
experiment, alpha particle was huge. Alpha particle is much bigger. Here we are talking about proton, electrons, right? They will not, stopped by a thin plate, by the D. They will go inside it.
Okay.
Again, I'll repeat it. I'm repeating myself. Everybody listen to it. Now you'll understand clearly. See here, the D's are there. They are metallic enclosures. Okay. So electric field has no effect inside the D. Okay. You want to increase the speed of the charge. Magnetic field cannot increase the speed because magnetic field cannot do the work. Kinetic energy can't change. So what happens is that inside the D, charge will experience only magnetic field. So inside the D, it will be a perfect semicircle. Okay. And if it is a perfect semicircle, I will exactly know how much time it will spend inside the D. And as soon as it comes out of the D, I will switch on the electric field in the direction of velocity. And when it comes out, electric field is in the direction of the velocity, the particle, the charge particle will accelerate. The force is Q into E. So it will create an acceleration. Velocity goes up. Okay. So velocity goes up every time the electric field is in the direction of velocity. The problem is on the top, the direction of velocity is this way. Bottom, the direction of velocity is the other side. So I need to keep on oscillating the direction of electric field. When the charge particle is coming out of the right hand side, the electric field should be in the direction of left hand side. When the charge particle is coming out of the left hand side, the electric field should be on the right hand side. So oscillator will do that work. Is it clear to everyone?
Sir, in between the D's also there'll be a magnetic field, sir?
Yeah, there is a magnetic field. But
won't that affect the movement between the?
It will affect. We are talking about ideal case. Experimentally, if you really want to design the cyclotron, there will be lot many other finer nuances. Okay, we are ignoring the effect of magnetic field between the Ds. The distance is very small between the Ds, and electric field is very high.
Yes.
But then yes, there will be effect. That is for sure. Any other doubt?
So between the two plates, the electron will try to go in a straight line.
Yes, that is the assumption here. Yes. We are assuming two things. Inside the D, it is semicircle, which actually is not true if there is a distance between the Ds. Second thing, we are assuming that distance between the Ds is negligible. Okay. Any other doubt?
Sir,
Jaldi bol, quick.
sir, the time period of the oscillator is also equal to pi m by qb.
That is very good question. Tell me how many times the magnetic field will switch in one time period, everyone.
Twice.
Twice or only once? Switching I'm talking about, switching.
Once.
It starts from here. The charge particle starts from here, let's say. It goes like this, goes inside the D, comes out. Electric field has to switch. Earlier it was like this. So it switches. Switch number 1. Then it comes back to the point wherever it started. So only once it switches. Okay. So time period of switching is equal to the time period of revolution actually. So 2 pi m by qb. So frequency of oscillator is the frequency of oscillation, which is 1 by t. So qb by 2 pi m. So if oscillator frequency is given to you, you have been given the time period of the circular motion itself, 2 pi m by qb. Okay? Clear about the oscillator frequency? All right. Now, if maximum possible radius, which is also radius of the D's, if maximum possible radius is r, okay, can you tell me with what kinetic energy a charge particle having charge q, mass m, okay, and the magnetic field is also given in a magnetic field B, what will be the kinetic energy if the radius is r? It will be when it comes out of the D. Everyone, do this. Anyone? So if the maximum possible radius is r, this will always be true. R is equal to mv maximum divided by qb. Okay, isn't it? From here, maximum possible velocity is qbr by m. Now, it does not depend upon the maximum possible velocity, doesn't depend on electric field. That is something surprising. Okay, so we'll talk about it. What is the reason and what will happen if you increase or decrease the value of E. But right now it is very clear that V max doesn't depend on the electric field. So kinetic energy, maximum kinetic energy is half m into V max square, which will be half m q square b square r square by m square, right? You can write it as q square b square r square divided by 2m. You don't need to mug up the formula as such. This is like just like a numerical, you can say. And every time somebody asks you what is the kinetic energy, maximum kinetic energy, you need to derive it quickly and then use it. Don't mug up each and every small formulas. So this is the value of the maximum kinetic energy that you can generate in a D. So the only one thing is valid here, as in one thing which is a property of cyclotron which will give you the maximum kinetic energy is the radius. Bigger the cyclotron, bigger is the kinetic energy. It only depends on the radius of the D's, nothing else. Everything else is the property of the charge or the magnetic field. Okay, B is a magnetic field. R, the geometrical property of the entire setup, only R on which it depends upon. And you can see it doesn't depend on the electric field. So if I increase or decrease the electric field, what will happen? Can anyone guess? What is the effect of having higher electric field or having lower electric field? What will be the effect? Final velocity doesn't matter. Final velocity will only depend on radius. So what is the problem here? What is
It will take more time to reach Vmax.
Correct. It will take more time. So if electric field is lesser and electric field is more, what is the difference in the path? How the path will look like?
The spirals will be more or less spaced out.
Correct. So all of you understand this. If electric field is lesser, the spirals will be very close to each other. It will take a lot of time to come out. If electric field is higher, spirals are far away. Okay. That's the only thing that will be happening. Otherwise, if you just talk about the final kinetic energy, it doesn't matter what you take. Any doubts in this cyclotron? Anyone has any doubts till now? Cyclotron is a very, very important topic. Everyone should be clear about it. Waiting for your doubts. No doubts? Doubtless? Where it is used? It is used in the subatomic particles laboratory, particles lab. Suppose you are one of the theoretical physicists who is exploring the fundamental particles, right? The smallest possible particles. So you are not content, or you don't believe that electron is the smallest particle. So you collide one electron with other electron and see what will come out. So all those things, for experimental purposes it is used. It might be used in for some other purposes also, but I'm not completely aware of that. But cyclotron, as such, the setup can be huge. Okay, there are few cyclotrons in US. The radius of the cyclotron can run up to kilometers. Okay, they are huge. All right, so we will continue from this one. So till now we have been talking about the force on a charge, right? Our contention till now was force on a moving charge. Okay, but then naturally charges don't exist like that. Naturally, charges won't exist as isolated particles. Okay, so all of that which we have learned, you'll not see any of it practically happening, okay, as in on its own. But then still there are situations in which charges are moving, and that is existing, in terms of the current. So current is a day-to-day life example of a moving charge. Okay, so can I get the value of force in terms of current? Okay, just like I got force is equal to QV cross B, can I get the value of force on this piece of wire? Let's say I have a piece of wire, a cylindrical wire like this, okay, on which current is going like this. This is the current. Magnetic field is magnetic field is coming out like this. So can I get the value of force in terms of magnetic field, current, and the length of this wire? Length of this wire is, let's say, L. L is the length. Fine. What I have is F is equal to Q V cross D. Okay. Try doing it. You can assume small n is number of free electrons per unit volume given to you. Area of cross section is A. Final expression should not contain this, but you can assume it, and then it will later on can get cancelled. Area of cross section. Try deriving it from here. You need to derive the force in terms of current. Everyone? No one? Acha, tell me what is Q? Total amount of free electrons, number of free electrons in this will be how much? Number of free electrons is N into
NLA.
A into L. Okay, so Q is what? That into charge E, isn't it? Charge of an electron into the number of electron is the total charge that is moving. With what velocity they are moving? Drift velocity. V drift cross with B. Okay, now this is the force, sorry, this is the force. Now I'll rearrange the term a bit. This will be NEA VD, and direction of the velocity, I'm giving it to the length. Length now becomes a vector quantity. What is the bracket term, everyone? What is this?
I.
I. So force is equal to IL cross B. Okay, so we have got the value of force in terms of current. This is much more practical to use than QV cross B, because current can be measured by using emitter very easily. So this is very useful formula. Here the assumption is the length vector is constant. It's not like a bend. It's not like this. Otherwise, the length over here, different direction, over there, different direction, over there, different direction. Okay. So if it is a bent, this thing, then what you do is that you divide the entire wire into small lengths. Okay. Then you say small amount of force on small length is I dl cross B. Total force will be basically the integral of this. When you integrate, take the components and then integrate. We'll be taking few questions on it, but if you want to directly use entire length IL cross B, length should be straight. Length cannot be bent. Okay, if length is not straight, you need to take components of the lengths, integrate, and then only you'll get the answer. Okay. All right, so let's take a numerical here. Write down the mass of the wire A to B is 500 gram. Okay. The length is given as 1 meters. It's a straight wire. Okay. It's a straight wire. Okay. So if magnetic field is given as 2 Tesla, and that is perpendicular to the wire, you need to tell me how much current should flow in wire. Okay, how much current should flow in wire to be suspended in the air? Okay, do it.
So I got disconnected. Could you go back to the previous slide?
Previous slide. This one. Will you understand all of this? Write down force is equal to IL cross B. Right now you just write down that.
So 1 second.
It's okay. I'll forward that thing anyways. IL cross B. This you have to use, okay?
Okay, sir.
Force on the length is this much. Shaumik got the answer. Aditya got something. both the Adityas got, Manjunath and Aditya C. If it is suspended mid-air, then the forces should be balanced, isn't it? What are the forces? One is gravity force, other is magnetic force. So both the forces should be equal and opposite. Net force should be 0. You just have to balance the two forces. This is the wire, let's say. Current is flowing like this, I. Gravity force is down, mg. Magnetic force should be up. Then only it will be balanced, right? So can you tell me the direction of the magnetic field, how it should be? Force is IL cross B. The length vector is the direction of current. Which direction magnetic field should be?
Outward.
Everyone.
Into the plane.
Into the plane, right? L cross B. L cross B. Align your hand in the direction of current. When you fold it, thumb should be upwards. So when you fold it, your fingers tries to go inside the screen. So the magnetic field has to be inside for thumb to be up. Thumb is the direction of magnetic force. So magnetic field is inside. Inside magnetic field is represented by the cross, like that. But that is not asked. So you just have to equate the magnitudes. The magnetic force is IL is how much? 1 IL into B. B is 2. They are perpendicular, right? Perpendicular wires. So L cross B is simply L into B. This should be equal to mg. M is 0.5 kg. G is 10. Okay. So current is 5 by 2. That is 2.5 amperes. Straightforward, it comes out. Okay. All right. So let's take another numerical here. So suppose you have 2 wires. You have 2 infinite wires. Okay, these are infinite wires. One of them is I1 current, other one is I2 current, same direction. Okay, the distance between them, distance between these 2 wires is D. D is a distance. You need to tell me what is the force by the first current on the second one and the direction of force also. Everyone. Magnitude and direction of force on I2 because of I1.
So the infinite wires, sir.
They are infinite. I will, how to show infinite? Like this dot dot. Yele. The hint is find the magnetic field of first wire on the second wire, then use IL cross B. No one?
So I2 can't be infinite, no, sir, because L will become infinite.
Okay, fine. So you find in terms of L. Assume that you're trying to find the force only on this length, this much length, L length.
Okay.
This is L. On this much length, what is the force? I will do it now. Magnetic field due to I1 on I2. How much it is? Tell me. D is what?
mu naught I
by
divided
2
by
pi
2
d.
pi d.
Mu naught I1 by 2 pi d, right? Infinite wire formula. Now the force on I2 should be due to the magnetic field outside I2 that is coming from I1, and this is what the magnetic field is. The direction of magnetic field is what on I2? Which direction it is?
Into the plane.
Everyone understand that? Align your thumb in the direction of I1, then fold your hands. Your hand fingers will hit the screen. It means that the magnetic field because of I1 goes into the screen. Got it? Everyone understand this, right? Magnetic field because of I1 will be into the screen like this. Everyone please type it. You have understood this. This is a magnetic field because of I1. Okay. All right. So if this is the magnetic field, the force I know is I L cross B. So which direction the force will be on this length? Direction of force will be what?
Left.
Okay. Others? Align your fingers in the direction of I2. Then fold it in the direction of B. Your thumb will point towards left. Okay. So this is the direction of the force. This is the direction of force on I2 because of I1. This is the direction of force. Now, what is the direction of force on I1 because of I2? Anyone can guess? According to Newton's third law, it has to be equal and opposite, isn't it? So it has to be like this. So basically, the parallel current attract. Parallel currents attract. What if I2 was in other direction?
Then they'll repel.
They will repel, correct. So anti-parallel current, anti-parallel or you can say opposite direction current repel. The direction of force would be then in this way if the current would have been in opposite direction. Okay, fine. So IL cross B, is length perpendicular to B in this case?
Yes.
It is perpendicular to B, right? So I can directly write it as I is my I2 here, L is L, B is mu naught I1 by 2 pi d. This is force. So force per unit length is constant, right? Mu naught I1 I2 divided by 2 pi d. This is the force per unit length between the two wires having current I1 and I2. separated by distance d. Okay, and this is actually a part of derivation. It was not a numerical as such. The title is, write down, force between two parallel currents. Okay. Should we take a break now or later on?
Sir, later.
Okay, I'll take a poll. It is an anonymous
So
poll.
later as well.
Later as well.
So later is when? What time?
Later as in 7.
Oh, now.
So tell me, A or B?
B.
Poll le. Everyone is picking B. Silent majority, huh? Silent. Okay, so this is what people are saying. Okay, so let's have a democracy for a few minutes. We will take a break now. Majority are asking right now. So right now it is 6:02. We will meet after 15 minutes, 6:17 p.m. Okay, all of you come on time. We need to finish this chapter. Probably it may get extended. All of you probably have to stay back this time for 15 more minutes, as in the last 1 hour, maybe 45 minutes or so. Only this time. All right then. See you after the break. All right, so all of you are able to hear me? Everyone is back? Hello, everyone. Am I audible?
Yes, sir.
Yes, sir.
Okay, so let's continue. So the portion that is left now is, yes, it is, it has to do with the effect of external magnetic field on a circular loop or any shape of the loop. What will happen to that current in a loop if external magnetic field is there? Now you know that whenever current is flowing, there will be a loop. So it is a good idea to understand what will be the effect on a loop because of the external magnetic field. All right. So this is what the next topic is. Write down. Torque on current loop. So the best example of that is the you know, when a coil is rotating between the magnets. So this scenario you have experienced many places. Generator is there, motor is there, AC DC generator both. So we'll be taking up that situation itself. So this is, let's say, north and this is south. Okay. The loop is this. Brush and this. Now I am putting a current on the loop using an external circuit. Okay. So current goes like this. It travels here and it goes like this and comes back. Okay. Let us say this is point A, this is B, this is C, that is D. Okay. Direction of magnetic field, can you tell me which direction it is? Which one? Magnetic field, either north and south poles are there.
Sir, on AB it's up.
From north to south.
Oh.
Magnetic field, I'm not asking magnetic field because of current. Magnetic field because of current won't have any effect on the current itself. It has to be an external magnetic field.
Yeah.
Okay. So the magnetic field will be like this, north to south. And it will be perpendicular to the side AB and CD, parallel to BC and AD. Okay. Now tell me, one by one we'll analyze the force on B to C, what it is. If current is I, what is the force? I'll tell you the lengths also. Let's say that this length is L1 and this length is L2. Okay, this one is L2. Tell me, what is the force? Magnetic field due to the magnet is B. B is a magnetic field. Now tell me, everything is given.
PC will be 0.
Little bit louder you have to speak.
Will it be 0?
DC or it will be 0.
It will be 0. The reason? current is parallel to the magnetic field. So IL cross B will be 0. Cross product between length and magnetic field will be 0 because they are in the same direction. Okay. Remember, the force is IL cross B. Length and magnetic field are parallel here. Force on C to D, what it is?
Out of the IL to B.
IL to B, everyone? I length is this C to D length is L2 and B. Is L2 perpendicular to B? Yes, CD is perpendicular to magnetic field. Direction, which direction the force will be? Align your hand in the direction of current, go towards B. Thumb is where?
Upward.
Outwards, out of the plane. So it will be out of the plane. Fine. So the force will be out of the plane like that. Okay. Then force on A to D. How much? D to A. D to A to D.
0.
0.
0 again, right? You can split D to A into two parts. This part and that part. Individually they are 0. Force on A to B. And in which direction?
Into the plane.
Into the plane, IL to B only. Right? It will be into the plane, IL to B. Like this. Okay. So total force on the loop is what? Sum of all forces.
0.
0. So we have determined that if magnetic field is constant, the force on this loop is 0. Okay. And what is the torque? Is the torque also 0? This is the rotation axis, let's say. About this axis it can rotate. Is the torque 0 or not?
IL1 into B.
What I'm asking, is the torque 0 or not?
No, sir, it's not 0.
It's not 0 because it will try to rotate like that, right? Torque because of that force is this force into its perpendicular distance, which is L1 by 2. So FCD into L1 by 2 plus FAB into L1 by 2. Both the forces are equal, which is IL to B into L1. This is the torque. So I can write down torque to be equal to I L1 L2 into B. Now L1 L2 is nothing but the area of the loop. So I can say torque is IA into B. A is area, B is magnetic field. And in terms of vector, you can, if you say A is my area vector, okay, you can write it as IA cross B. It's a cross product between area and the magnetic field. Now this you have analyzed, you have found out torque is equal to IA cross B for the rectangular, the rectangular loop. But is it true only for the rectangular loop or any shape and size of the loop? This is what we'll be discussing next. But have you understood this particular scenario here, everyone? Okay. All right. So, do you guys remember the torque on the electric dipole? What was it? P is the dipole moment. P
minus
E. Kya minus those? P cross E. P cross E is the torque. You guys remember this or not? You go to chapter number 2, you forget chapter number 1. Like that. P cross E is the torque, right? And if if I say that electric and magnetic field, they are the two sides of the same coin, then the formula for the torque in case of magnetic field should be magnetic dipole moment cross with the magnetic field B, because the formula should look similar. Now, if you compare these two and the formula which you have just derived, IA cross B, you will come to a conclusion that magnetic dipole moment can be written as current into area vector. Okay, so this is a definition of magnetic dipole moment. Write down. Magnetic dipole moment. Okay. Now let us see whether whatever we have derived, torque is equal to, now the final thing is torque equal to M cross B. Now we'll see whether this is true only for the special case like this, or any shape and size of the loop. I can write down torque equal to M cross B, where M is current into area. Let's see that. Now let's assume an irregular shape loop. Okay, this is the loop, let's say, on which, what happened? Okay, on which the current is flowing like that. Fine. And let's say magnetic field is present in this direction. I'll not draw such big lines, just I'll represent it. This is how magnetic field is. Okay, like in the earlier case. Now look at it, what we'll be doing here. You will assume it like that. I'm just going to show these two things here. Okay, now you assume that this entire thing is made up of small rectangles like this, one rectangle stacked over above like that. The thickness of rectangle is very small. For the understanding sake, I am making the thickness little more. Okay, but the idea should be clear here. Look at it. I will say current go like this in the direction of the actual current, goes like that, comes back. This is how current comes back from here and then goes like that. But you know, these two current don't exist. This doesn't exist, that doesn't exist. This and that, they exist. So what happens is, in order to make sure that this imaginary current get cancelled away, I need to assume an opposite current in the above rectangle. So opposite current goes like this, like that, this and that. And then I will consider another rectangle here like that. Opposite current goes like this, then here, here, there. Okay, so it's a concept of calculus only. I'll assume very small rectangles like that, and I will say that the entire loop is made up of multiple rectangles only. Are you able to understand what I'm trying to explain here?
Yes, sir.
Okay,
Yes, sir.
so I can say that any irregular shape loop can be considered as collection of rectangular loops of negligible thickness stacked one above other. Okay, so the total effect will be just, you know, you just need to just add it up. So torque on this one plus torque on that one plus torque on this one, then torque on that one. So you can see that torque will be equal to M1 cross B. M1 is dipole moment of this rectangle plus M2 cross B, like that. So when you add it up, torque will become M1 plus M2 plus so on cross B. So total dipole moment M cross B it will be. Okay. So it doesn't matter whether the loop is regular or irregular, whatever shape and size of the loop is, torque will be equal to M cross B. Okay. So this is the derivation of the fact that it is a general formula. And one more point of caution here, that loop need not exist in a single plane. Loop need not be in one plane. Okay, it may happen that part of area is having I direction and the other part of the loop is in j direction. So this is the area vector. So magnetic dipole moment will be current into that I A1 I cap plus I A2 j cap. So simply instead of M, you have to put the value of this and take a cross product with B. You'll understand more of this when you solve few questions. But right now, is the formula clear to everyone? Everyone is able to understand the formula? Any
Here's
doubt?
the direction of area vectors into the plane.
Very good question. The answer to that is right hand curl rule. Align your right hand fingers in the direction of current, fold it in the direction of current, thumb is the direction of area. Okay, entire chapter is right hand curl rule. You don't need to do anything else other than using right hand for the direction, any direction. Any other doubt?
So can you repeat? It was not clear.
So what I think Tripan was asking was, what is the direction of area, or what is the direction of magnetic dipole moment M? Right? Dipole moments M's direction is the area direction. And area direction, how to find? There are two directions of any area. Like if I draw a circle like this, it can be either inwards or outwards. So what I'm saying is, curl your hand in the direction of current, thumb is the direction of area. So tell me, in this case, what is the direction of area?
Outwards.
Outwards, right? This is what I was saying.
Okay,
Any other doubt? No doubts? No one? All right. So we will conclude this thing by saying net force, write down net force on any loop, any current carrying loop will be zero in a uniform magnetic field. In a uniform magnetic field B. Okay. Force is zero, but torque is not zero. Torque is equal to M cross B, where M is current times area vector. All right. Fine. So let us take a question from your NCERT. Right. In fact, it's a huge question. I will directly take it up. I'll take a screenshot and put it up here. Just give me 1 second. Bhautiki. Bhautiki is the Hindi of physics. Don't open your NCERT. Okay. Where it is? This one. This question. By the way, one small thing, if number of turns is n, magnetic dipole moment will be NIA. N is number of turns. We were assuming total number of turns are 1 only, but if total number of turns are more than 1, you have to multiply by that to find the magnetic dipole moment. Do this. Part A and B will be straightforward. Okay, solve it completely, all of you. A and B. You can tell the answers now for A and B first. If you are able to solve this question your own, you have understood everything about the dipole moment as of now. Should I attempt now or should I wait?
1 minute, sir.
1 minute. Time starts now. Okay, so I think I have to solve it. No one is getting only Ravi Kiran got something. Yes, Ravi. Part A is correct. Others, what are you doing? Magnetic field is mu naught number of turns I divided by 2R. It's a circular coil. Okay. So mu naught is 4 pi into 10 raised to power minus 7. Number of turns, how many? 100. Current is what? 3.2 divided by 2 times R. R is 0.1. Okay. This will come out to be 2 into 10 raised to power minus 3 Tesla. Okay. All right. So B part, magnetic moment. How to find out the magnetic moment? M is equal to N I A. All right. N is 100. Current is 3.2. And area is what? Pi r square. Pi into 0.1 square. How much is this? This is 10 ampere meter square. Dipole moment's SI unit is ampere meter square because it is current into area. Okay, these are the two parts. Now, C part. What is the magnitude of torque on the coil in initial and final position? What is initial and final position? Coil is placed. By the way, it is your NCERT book question. Okay, so you should not find an excuse that, oh, this is a higher order question, I need not be solving it. This is your NCERT book question. I've taken a screenshot in front of you. Okay, and board exams are becoming more and more numerical oriented. Okay, last year the paper was of the level of between CET and mains itself. So you should be able to solve these questions. Pay attention and attempt all of that. Coil is placed in a vertical plane, field to rotate about the horizontal axis. Where is the horizontal axis? Horizontal axis is this. About this axis it can rotate. How it will rotate? It can rotate like that. Fine. A uniform magnetic field 2 Tesla in a horizontal direction exists. So 2 Tesla exists in this direction, horizontal direction. We need to draw the diagram, okay? Without drawing the diagram, don't attempt any physics question. Axis is the direction of field, like that. The coil rotates by an angle of 90 degree under the influence of magnetic field. Right now, coil is like this. It has current like that. And then when it rotates, after rotation, what will happen to the coil? Coil will become, right now it is vertical. Coil will become, after 90 degree, horizontal. Okay. So now answer C part. Torque is M cross B. Okay, Srishti has answered. Others? Aja, guys, wait. Hold on. The direction of magnetic field is not correct. What is written is, sorry about that, direction of the, it is horizontal and along the axis of the coil. Axis of the coil is coming out of the screen. Okay, so magnetic field direction is like this. It comes out of your screen. From here, It comes out of the screen. Fine. Sorry about that. So now tell me, what is?
Sir, but it says the axis coincides with the diameter, no, sir.
Where does it say?
The first line.
Horizontal direction exists such that initially axis of coil is in direction of the field. Where did it coincides?
So the first line.
That is the axis of rotation.
Yes.
That's the axis of rotation. This is something else. This is
For
different.
axis of the coil, we should consider the area vector.
Correct. So this is the coil. Axis of rotation is different. Free to rotate about a horizontal axis. About a horizontal. If it is written about the axis, then that is different. It says about one of the horizontal axis which coincides with its diameter. The axis is always perpendicular to the coil. But then yes, I can understand they should not test you on English here, but this is how it is. So initially, what is the angle between area vector and the magnetic field? Initial?
0.
0. Final?
90.
90. So initial torque is 0. Final torque is mb sine theta, which is nia into b. What is that equal to? You found out? Anyone? Someone is getting 20. Why you guys are not able to get this? Don't understand. Directly to substitute the formula m cross b. So theta is 90 degree. So m is nia. Nia into b into sine of 90, which is niab. So this is 20 Newton meter. These are the three parts. Now the d part is the main one. Okay, d part. You have to find angular speed by the time it becomes horizontal. Now tell me one thing. Is angular acceleration constant or not while it is rotating? Everyone. Is alpha constant?
Yes.
Can I use omega square is equal to omega naught square plus 2 alpha delta theta? Can I use this? This is valid only when alpha is constant. Is alpha constant? Acha, is torque constant throughout the rotation?
No.
Torque constant? Does torque depends on amount of rotation?
Yes.
Torque depends on theta, right? So torque is not constant. So even alpha is not constant. You cannot use this equation. Then what you have to do? Use calculus. Write alpha as d omega by dt. This can also be written as omega d omega by d theta. And yes, it is again NCERT book question. Do it now. Try doing it. How to get alpha? Anyone? How will you get the value of alpha?
Torque is equal to I alpha.
Torque equal to I alpha. You get alpha. Alpha you should get in terms of theta. And then use integration. Should I do it? Acha, tell me, if coil rotates by an angle theta, then what is the angle between M and B?
Theta.
Okay, I'll do it now, everyone. So if the coil rotates by 90 degree, angle is 90 degree. If coil rotates by angle theta, angle is theta. So torque is equal to mb sine theta if it rotates by an angle theta. So this is NIA, which is B, which is M, sorry, NIA is M. MB sine theta is torque, which is equal to I times alpha. Okay, so alpha is equal to N, this I is current, okay? So the other I is moment of inertia. NI should I write? NIAB divided by moment of inertia times sine theta. This is alpha. Now alpha I'll write it as omega d omega by d theta. How it comes? By alpha is d omega by dt. I multiply and divide by omega d omega. Sorry, d theta. Rearrange it, you'll get d theta by dt into d omega by dt, d omega by d theta. So this will be omega d omega by d theta. Okay, so this equation alpha is d omega by dt is in terms of time and omega. This one is in terms of omega and theta. So I am getting alpha is in terms of theta. There is no time here. So I'll write in terms of theta only alpha. That is why I'm using this. NIAB by I sine theta. So omega d omega is equal to NIAB by I sine theta d theta. Now you integrate it. From 0 angular velocity to omega, theta goes from 0 to pi by 2. You will get the value of omega from here. Everybody understood? The last part was a little tricky. Okay, let's move forward now. All of you. Right. Now we all know the fundamental. Is it raining in Rajajinagar?
Yes, sir.
It's raining heavily here also. Fundamental unit in electrostatics is what? Charge. Next fundamental unit is dipole. Okay, so it makes sense to write the value of electric field as a function of the fundamental unit charge. And this is the fundamental equation, right? But unfortunately, when we talked about the magnetic field, we wrote the formula of magnetic field in terms of what? In terms of current and the length element, right? Or you can say it is a function of IDL. Let me close the window. Its sound is coming. Okay, so but is ideal the fundamental unit of the magnetism, or what is a fundamental unit? Fundamental unit is monopole there? Can north pole exist in isolation?
No.
Then what is a fundamental unit in magnetism?
Dipole.
Magnetic dipole. Magnetic dipole. And you already got introduced to it, right? So fundamental unit is magnetic dipole. Then why we are writing the formula in terms of I and dl? In electrostatic, we wrote all the formulas in terms of fundamental unit. So we should write magnetic field also in terms of magnetic dipole moment, right? If magnetic dipole moment is a fundamental unit, so this is what we are trying to do next. All right. But you know why we have written in terms of ideal? Because it was easy to find. Biot-Savart law is for ideal. But when you go into the fundamental units, ideal is not a fundamental unit. Fundamental unit is magnetic dipole moment. So now we are trying to write equation in terms of magnetic dipole moment. Okay, that will be our fundamental equation of magnetism. So write down the thing is we are trying to write circular current loop as a magnetic dipole. Now it is first write down and describe it. See, this is little different way of deriving. Here what I am going to say is that I already know the magnetic field due to the circular current loop. Okay, I already know it in terms of current, radius, and the distance from the axis. I already know it. Okay, so what I'll do is that I will try, write down, I will try to write magnetic field B of circular wire in terms of magnetic dipole moment M. Okay, and once I get the formula in terms of M, that formula is not only valid for the circular current loop, it will be valid for any dipole moment M, because M is a fundamental unit. That M could be because of the circular current loop, could be because of rectangular loop, could be because of the magnet, could be because of anything. As long as the value of M is same, it does not matter from where it is coming from, because it is a fundamental unit. Are you getting what I'm trying to say here?
Yes.
Again, I'll repeat. See, the fundamental formula should be in terms of magnetic dipole moment M. But I don't know what is that formula. But what I know is the magnetic field due to a circular loop. So if I transform that formula and arrive at a formula in terms of magnetic dipole moment, then that formula should be valid for any dipole moment M, whether it is coming from circular or rectangular or magnet or any other thing. It doesn't matter then, because it is a function of M only. As long as I know what is M, it is immaterial from how M is coming from. Okay, so now for a circular loop at a distance x, let's say this is a circular loop. Circular loop is there current is I, and at a distance of x from the center along the axis, let's say radius is r. What is the magnetic field? We have derived it, all of you. B is equal to what?
So mu naught ideal by 4 pi r square.
Okay, mu naught I r square. All of you write down mu naught I r square divided by 2 times x square plus r square raised to power 3 by 2. Okay, getting it? Suppose number of turns are n, then I have to multiply with n if number of turns are n. Okay. Now I want you to write this magnetic field in terms of dipole moment m and x. And just like in electrostatic dipole moment, you can assume that x is very large compared to r. Can you try doing it your own? It will be very nice if you can arrive yourself. Transform this formula in terms of m. Right now it is in terms of current r. R should not be there in the equation. No one? Anyone got it? Ayush, did you get? Remember what was m? M was n I into a. A over here is pi r square.
Sir, mu naught m by 2 pi x cube.
Okay. So let's do it now. Multiply and divide by pi. So you'll get mu naught by 2 pi n I pi r square. You understand, right? Why I've multiplied and divided by pi? So that in numerator m will come. Okay. 2 times. Now x is very large compared to r. So x square plus r square is x square only to the power 3 by 2 roughly. Fine. So I can write this as 2 is not there now. So I'll write it as mu naught by 4 pi into 2 times magnetic dipole moment m divided by x cube. Now tell me, is it clear to everyone? Clear to everyone? Type in yes or no. You, if you delay, I have to then extend the class.
Yes, sir.
Quickly. Okay. So this is the magnetic dipole moment, and this is what along the axis, not the magnetic dipole moment, magnetic field along the axis of dipole M. Okay. Now Do you remember along the axis what was the electric field due to the electric dipole? What is the formula? You remember? 1 by 4 pi epsilon naught multiplied by
P by R square.
2p by x cube. This was the formula. Look at these two formulas. Are they look very similar or not? These two. Right? They are looking very similar. Instead of 1 by 4 pi epsilon naught, mu naught by 4 pi. Okay. So this is another confirmation of electric and magnetic fields are two sides of the same coin. So now equatorial plane electric field due to a dipole was 1 by 4 pi epsilon naught minus p by x cube. So how much should be the magnetic field in the equatorial direction? This is axial. Equatorial will be here, draw the line like this at a distance r from here. Sorry, not r, at a distance x from here. What will the magnetic field correlate this equation with the formula?
Mu naught by 4 pi minus m by x.
Correct. Mu naught by 4 pi into minus m by x cube. You don't need to derive it. Now, since you have got the magnetic field in terms of dipole moment m, you don't need to know radius, you don't need to know current, you don't need to know number of turns. So all of these things are immaterial now because magnetic dipole moment is a fundamental quantity. If you tell me what is a magnetic dipole moment m for any situation, I'll just substitute the value of m here and get the magnetic field. I don't care whether it is from the coil, from magnet, or any other thing. Okay, so this is how you derive the magnetic dipole moment for a current loop, and the final expression is valid for any dipole moment. It doesn't matter loop or not. All right, so just like we have in electrostatics, we introduced charges being the fundamental particle or the fundamental thing for the electric field. Here we have introduced magnetic dipole moment, and we know that smallest possible charge is what? Anyone? Charge of an? You guys forget everything.
Electron.
Electron. Charge of an electron is the smallest possible charge. Now we have defined magnetic dipole moment. So can you tell me what is the smallest possible magnetic dipole moment? Magnetic dipole moment is a fundamental quantity. So let's find out what is the smallest possible magnetic dipole moment. So can you think of smallest possible current loop? What it should be? Any charge moving in a circle is a current loop. That's the hint. What is the smallest?
Radius of hydrogen atom.
What? Say it again.
Radius of hydrogen atom.
I'm asking magnetic dipole moment, not the radius. What is the smallest possible magnetic dipole moment? That will be, you're correct, in fact. The electron which is revolving around the hydrogen atom will have the smallest possible magnetic dipole moment. Okay, so next topic is exactly that. We are trying to find out what is the value of this. Okay, so write down the heading magnetic dipole moment of a revolving electron. Yes, Shankin. That's what. Fine. So all of you draw one hydrogen nucleus. Let's say this is the hydrogen nucleus. Okay. And the electron is revolving around it. Now, electron in ground state or excited state? Smallest possible dipole moment. Ground state,
Ground
Does it
state.
right?
matter?
It matters because radius changes, no? Then dipole moment will increase.
Yes.
So electron in the ground state will have the smallest possible dipole moment. So let's say the radius in the ground state, I'm assuming you have done the atomic structure chapter in chemistry. This radius is R, let's say. The ground state radius is R. Charge of an electron is E. Okay. All right. Can you find out what is the dipole moment of this revolving electron? The formula is again Ni into area A. Number of turns is 1 only, so you just have to multiply current with area. So you need to find what is the value of current for this revolving electron. Try doing it. Bohr's model you remember, right? Bohr's model, what does it say? MVR is equal to, you guys done this or not?
Yes, sir.
Here n is equal to 1. Or you can find in terms of n only. At the end you put the value of n to be equal to 1. What is the value of current? I is what? E divided by the time period of revolution. Time period of revolution is what? 2 pi r by V, isn't it? So it will be EV divided by 2 pi r. Okay. Now, magnetic dipole. Acha, by the way, when we talk about subatomic particles dipole moment, we represent it with mu. Okay, just like a special respect we give to them. Mu is the dipole moment of the revolving electron is equal to EV divided by 2 pi r into area, which is pi r square. Okay, so 1 r cancels away. You will get pi E VR. A pi also get cancelled away. EVR divided by 2, right? EVR by 2, correct. Now I know that MVR is equal to NH by 2 pi. So from here, I will get V into R is equal to NH by 2 pi M. Okay. So the value of mu will come out to be ENH by 4 pi me. So this is the dipole moment of a revolving electron. When you put n equal to 1, you'll get the smallest dipole moment in the world. And there is a name to it also. This is called Bohr magneton. The smallest possible dipole moment is Bohr magneton. So yes, when you put n equal to 1, the value of mu comes out to be this, 9.27 into 10 raised to power minus 24 ampere meter square. So if by any chance in any numerical you get a value of dipole moment less than this, that's a wrong answer, because less than this dipole moment doesn't exist, and every dipole moment will be integral multiple of this, just like charges. But then this unit is so small that anything you divide, any value, if you divide it with this, integer will automatically come out, because this is 10 is a minus 24. So very, very small unit. Okay. So, there is one more topic, but that we can do in the next class. That is moving coil galvanometer. It'll take at least 1 hour. I don't want to hurry up. So we will be solving questions now on whatever we have done. Tell me.
So you said that mu doesn't, it matters if it's ground state or excited state. But then your mu doesn't depend on radius. So
mu depends on n, right? See, there is n.
So n is the number of electrons, right?
No. N is principal quantum number.
Oh, okay.
अरे सब भूल गए तुम लोग. Atomic structure. This what is this? N, principal quantum number, excited state, which state the hydrogen atom's electron is.
Okay, sir.
So we will now solve questions. No point continuously running behind theory one after the other. Moving coil galvanometer will be taking up in the next class. Okay. In the next class, we'll be taking a moving coil galvanometer. There are a lot of finer details there. We'll be talking about how you can convert galvanometer into voltmeter, galvanometer into ammeter also. So we'll take 1 hour. So that will take up in the next class. Right now, those who want to leave can leave. We'll be taking up higher order questions on whatever we have done till now on this chapter. Okay. I'll wait for 30 seconds. All right, so only one person left. If only one person left, I should find out. No, I'll leave it. All right, so let's take up the questions now. We will take up. Where is that gun wala question? This one. In this chapter, the tricky question is a myth. Okay, almost every question you can categorize into 3 or 4 types. Just solve 30 to 40 question on this chapter. That's it. Okay. It'll move in a helical path, right? What are you talking about, Aditya? Focus on this question. Acha, this one, sorry. I misunderstood your doubt. So energy of 2 keV, it means what? How many joules? 2 into 10 raised to power minus 3 into 1.6 into 10 raised to minus 19. This much joules of the kinetic energy. This is the kinetic energy of the electron.
Why minus 3, sir?
What?
Why minus?
Sorry, plus 3, not minus 3. This is half mv square.
So S doesn't lie in the same plane, sir.
What? Say it again.
So S doesn't lie in XY plane.
No. Why you say so?
So because the force will be perpendicular to both V and V.
So what? It will move in a helical path. It will, when it completes a circle, it will hit the plane, right? It will move parallel and then come back and hit the plane.
Okay.
Should I do it? Parallel to magnetic field, the speed is V cos 60. Perpendicular to magnetic field, it is V sin 60. Okay. So it will move in a circle with center lying on the line of magnetic field, all right? It will go like this and hit the spot S. It will be able to hit the spot S only when the distance of S from the initial point, what is this? Sorry. Distance of S from the initial point is integral multiple of the pitch. Let's say this is P pitch and this is another P. After 2 times, it makes, after completing 2 circles, it'll come back to the same line. So this distance should be equal to 2 times pitch. Okay. So like that, you can say that only when it will hit S, when the distance is integer multiple of the pitch, otherwise the it is electron, right? So electron will not come, electron otherwise won't come and hit this line. Electron will hit the line only when it completes the circle. Every other time it is either above or below the line. I hope it is clear. Okay. Right. So the time period of revolution is 2 pi m by qb. It doesn't matter which direction, velocity, whatever it is, time period will be this. And in this time period, the pitch should be equal to 2 pi m by qb times v cos 60. This is the pitch. And we discussed that the integer times this pitch should be equal to distance g to s, which is 0.1. Okay. And you need to find minimum value of b. So for a minimum value of b, what should be the condition? Anyone? If b is minimum, pitch is maximum. if pitch has to maximum, at least the distance G to S should be equal to 1 times the pitch. Okay. So 2 pi m by QB into V cos 60. The pitch should be equal to 0.1 for maximum value of B. All right. Now, don't try to find velocity from here because you need to substitute for m into v, right? M into v. So basically, kinetic energy is given as this. So m into v is momentum. Momentum can be written as root over 2m into kinetic energy. Instead of kinetic energy, substitute this. Take a square root after multiplying 2m and substitute directly in terms of substitute directly for m into v from here. Okay, so this question is more or less mechanics question. Other just one formula is utilized here for the magnetism. Just go through it once and let me know, is it clear or not? All of you able to understand this? Any doubts, please ask.
Sir, why does it take a helical path?
Because the velocity component is there along the direction of B.
Yes.
Any other doubt? Electron are traveling along x-axis. If the angle is 90 degree, then it will not take helix. It will go in a circle only. But angle is 60 degrees. So it will go along the magnetic field as long as moving and also move in a circular path. No doubts, right? अरे बोलो भाई कुछ. Shankin.
Also understood.
Shankin.
Clear, sir.
Understood? Okay. See, yeah, this one was a little bit twisted. So it's fine. There was one more question. This one. These are the descriptive questions when JEE Advanced used to be a descriptive paper. Solve this. Step number 1 is to get the magnetic field at point P. Force is equal to mass and acceleration, and then you'll get the acceleration. Force is QV cross B. First do the part A and answer. Part B we can do later on. Okay, so I can see some of the answers. Good to see that. So I'll solve it now. Part A.
1 minute, sir.
Acha. I'll just draw the diagram. No doubts, these questions you will find it difficult initially, but that's fine. You need to get through that. Okay, so now I will solve it. This one is Mn. Current is flowing like this. We need to find magnetic field over here. Now magnetic field will be because of the straight section Nm and a curved section Mn. So is the magnetic field by Nm and the curved section circular arc Mn are in the same direction or in opposite direction? This magnetic field and that magnetic field over here, same direction or opposite one?
Opposite.
They are opposite, right? Which direction the magnetic field is due to the straight section? Due to the straight section, which direction?
Into the plane.
Into the plane. Due to the curved section, out of the plane. Okay, so total magnetic field will be difference between these two. Fine. So this is the, whenever we see a finite wire, we have to drop a perpendicular, find this distance and these two angles. These two angles over here are 60 degrees. Okay. So perpendicular distance is what? D is, this is radius R, cos 60 is a perpendicular distance, which is R by 2. Magnetic field is mu naught by 4 pi into D, that is R by 2 into sine of theta 1 plus sine of theta 2, which is 2 times sine of 60. This is the magnetic field due to the straight section B1. Okay, I'm just going to leave it like this. B2. Achha, this one is which direction we said? Minus K, right? This is minus K. B2 is due to this curved section. Curved section makes 120 degree, which is 2 pi by 3. So this is 1/3 of the circle, right? So due to the full circle, the magnetic field is mu naught I by 2 times R. 1/3 of that is the magnetic field due to the 1/3 part of the circle. That in K direction. So total magnetic field B is minus automatically takes care that you need to subtract. Okay. So vectorially B1 plus B2 you'll get. Minus is there, B1 minus K cap. So when you add, they'll subtract actually. Okay. So the velocity is given in which direction? It along NP. So it is going like this, where this angle is 60 degrees. Okay. So V cos 60 I cap plus V sin 60 J cap. They're testing your vectors knowledge also here. So the force will be QV cross B. Take a cross product. This B is along K, right? So take a cross product, vector cross product, then find the magnitude of the force. That should be equal to mass into magnitude of acceleration. So acceleration is magnitude of force by mass. So all of you understand the part A? Part A, any doubts?
No, sir.
Okay, now do the part B. You don't need to exactly find the value, okay? So if you write the equation like this, you can tell me that you're done. Isn't B1 supposed to be UI? What do you mean, Shankin? Acha, I, current. Yeah. That's fine. Put a value of I here. There's a current. B part. What is the force? The value of force is what?
BQV root 3 by 2 K cap.
No. Anyone else? What is force? How much is the force?
On the loop.
What we have studied just now about the loop. Force will be तुम लोगों का ध्यान कहाँ रहता है भाई? कहाँ गया loop? Loop. Where we have summarized. क्या लिखा है यहाँ पे? Read it. What is written? The force should be 0 because magnetic field is uniform. Any kind of loop, whatever it is, as long as the field is uniform, the net force should be 0. Okay, this is the part 1 of the B. Now tell me what is the torque. How to get the value of torque? Torque is what? What is the formula? M cross B. And what is M? This area you can find out or not? You know how to find the area? You don't know?
Yes, sir.
Pi r square by 3 is a sector area. You remember sector area is half r square theta. Okay, theta is 2 pi by 3. So pi r square by 3 is area of sector minus area of this, whatever, this is a triangle, d is a perpendicular distance, half base into height. So that, this one will give you area of the loop, A naught. Okay, so current into A naught, and this is in the direction of, this is K direction. Okay, cross with magnetic field is also in K direction, is it? No, wait. No, this is the external magnetic field you have to use. This one, BI. So K cross I is J. I A naught B J. This is the answer for the torque. You should not use magnetic field created by the loop to find the torque on the loop, because that will not create anything. You have to use the external magnetic field which is given to you. Just go through it once. Let me know if you have any doubts. Anyone has any doubts in this question? Quickly type in whether you have understood. It's an J advanced question. Okay, you can't directly just, it will not be of just formula substitution. Little bit twisting will be there. Okay. If you have not understood completely, just after the class, go through it once. Right now, everything is fresh. If you go through it once more, it'll be clearer. So this is the true and false. So all of you can quickly answer to me. There are 4 statements. Mark it true or false. Answer it quickly. First one is no net force, uniform magnetic field. True. Just now we discussed. There is no change in the energy. Work done is 0. Change in energy is also 0. True. This will be a circle. No. It makes some angle which is not 90 degree. So this is false. Electron proton will have same radius if they have the same kinetic energy. Radius is what? mv by
Depend on mass also.
qt. How can you write this formula in terms of energy? It can be written as 2m into kinetic energy under root of that divided by qb. Now you've written this in terms of energy, but still mass is coming in. So this is again false. You should not answer 4th question by by looking at this formula. Look at this formula. In terms of kinetic energy, you should write. Okay, so straightforward question. Let's take up something which is a little bit uh, this one. Okay, fine. No, let's do it on today's topic only because that is not very clear as of now. This one. Again, I am reasonably sure that you'll not be able to solve it completely. And even I would not have been able to do this when I would have been at your age. But then try it out. Try doing it till wherever you can. How to get the value of current? Charge Q distributed on the rim. That is Q by time period. We found out, right? The current value due to the charge Q rotating in a circle already. Q divided by the time period. Time period is 2 pi by omega. This is one of the tricky questions in this chapter. So I am only doing questions which are very tricky. Do not judge the chapter that chapter is difficult. No, no, no. Okay, chapter is very simple. When you solve questions your own, 90% of the questions will be straightforward. I am only picking the questions which are difficult. All right, so I'll do it now. Nobody is able to
Oh.
solve it.
1 minute, 1 minute.
Draw the free body diagram, balance the force, balance the torque. That's all. Tensions are not equal because there is a torque acting due to the rotation of the coil. Okay, all of you pay attention here, everyone. Initial tensions are T naught. So basically, the total force acting upwards was 2 T naught. Now it will be T1 and T2 when it has started rotating. So the total mg force earlier was balanced by 2 T naught. So T1 plus T2 will be equal to 2 T naught only. The reason is T1 plus T2, right now also it is mg itself. And the earlier it was T naught plus T naught, so 2 T naught. Okay, so the first equation is T1 plus T2 is equal to 2 T naught. This is the first equation, force balance. Now next up is torque balance. Okay, so now this you should all read this one, that torque because of the magnetic field is a couple. Couple is a special kind of torque whose value doesn't depend on about which point you're finding. Its value will be constant. So do not worry about which point torque is equal to m cross b, about which axis it is. Every time it will be the same value. Okay. So the torque due to the magnetic field. Okay. Tripan got it. Tripan got it. Torque is equal to IA cross B. Over here, area vector is this and B is like that. So they are making 90 degrees. So IA into B is the value of torque. Which direction the torque is? Which direction the torque is? A cross B. Which direction? Align your hand in the direction of area, that is right hand side. Fold it upwards. Thumb is pointing towards you. Okay, that is the direction of torque. Fine. So this is a couple, IA into B. I is what? Q divided by time period, which is 2 pi by omega. So Q omega by 2 pi into A into B. Is radius given or area is given? Or nothing is given?
Radius is given.
Wheel of radius
कहाँ है radius?
on the first line.
Radius is given. So A is pi r square. So 2 Q omega, pi will get cancelled away, r square b by 2. This is your torque. Okay. Now balance the torque about anything. If you you can find the torque about this point. About that point also torque because of magnetic field will be this only. Okay. So T2 into the total length is D. T2 into D minus Q omega. It has to be minus, otherwise they will not be balanced, right? B by 2 should be equal to 0. So you'll get torque T2 and then you get the value of torque T1. So whichever is higher, that tension should be, breaking tension is this, right? So tension should be less than or equal to 3 T naught by 2. Both T1 and T2 should be less than this. So using this inequality, you will get the value of omega. This is omega naught. You'll get the value of omega naught. Okay, this one was little trickier than the usual ones, and this is only one of its kinds. You will not find these kind of questions routinely. All right, so that's it from my side today. We will continue with this chapter. Probably we'll spend 1 more hour talking about the galvanometer and how it can be converted into voltmeter and ammeter. And then we will start, what we will start in NAFL. Which chapter is going on, guys? No one from NAFL is there. Shankin, what is going on in NAFL? This one only, this chapter. Okay. Anyway, so I can start anything, right? Then. So I'll pick a chapter and we will take it up next class itself. So we'll finish this chapter and start a new chapter the next class. Bye for now.
Thank you, sir.
Thank you, sir.
Thank you, sir.